Hi there, this is Simple Harmonic Motion, Lesson 5, the simple pendulum. So start a question, if you want to pause and have a go. The Earth moves around the Sun in a circular orbit with a radius of 1.5 times 10 to the 8 kilometers. What is the Earth's approximate speed? So the Earth travels around the Sun in a mainly circular orbit, so we can use the equation V equals 2 pi r over t. So we've got 2 pi multiplied by the radius of the circle, which is 1.5 times 10 to the 8. And then times 10 to the 3 on top of that to turn it into meters. So times 10 to the 11 meters divided by the time period. So it's 365 days. And there are 86,400 seconds in each day. And that comes from, I'll do the full thing. We've got 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, which gives the 86,400. That gives a velocity approximately equal to 29.9 kilometers per second. Okay, let's move on. Let's do the next one. Or let's get some new information. So the simple pendulum. So it consists of a point mass, which is the orange thing, undergoing small oscillations, as you can see in the GIF file on the left, suspended from a fixed point by a massless, inextendable thread of length L, obviously encompassing a gravitational field. And the time period T is given by T equals 2 pi square root L over G. So if you want to write that down, pause, make some notes. Time period is obviously measured in seconds, length's in meters, G is meters per second squared or newtons per kilogram. Ready to move on? So here's a question. If you want to pause and have a go. It's going to calculate the period of a pendulum of like 15 centimeters on the Earth's surface. We'll do that one first. So time period T is equal to 2 pi square root L over G. So let's put some numbers in. 2 pi multiplied by 0.15 meters divided by 9.81. Calculate that, gives a time period of 0.78 seconds. Could put 0.8 seconds if you wish, one significant figure. So I'm going to get rid of that and do part B. So B, the pendulum length required to give a period of 2 seconds on the surface of the moon, where G is 1.67 meters per second squared. So same equation, 2 pi root L over G. We need to find length, so I'm going to square everything. So T squared is equal to 4 pi squared L over G, and then rearrange to find the length. So we've got T squared times G, sorry, the pi is obviously squared, divided by 4 pi squared. And that'll give us the length. So let's put some numbers in. So the time period is 2 seconds, so square that equals 4 times G, 9.81. Sorry, 1.67. And then divide that by 4 pi squared. Gives a length of 0.17 meters. Let's do another question. Hopefully that went okay. So this one, let's pause and have a go. A simple pendulum has a time period of 1.42 seconds on Earth. The gravitational field strength at the surface of Mars is 0.37 times that at the surface of the Earth. What is the time period of the pendulum on Mars? So we've essentially got the same pendulum, but it's going to be used in 2 different places. So I'm going to get the equation, t equals 2 pi root L over g. And we want to see how t and g are related, so I'm going to square everything. So t squared is 4 pi squared L over g. And what I can see is that time period squared multiplied by gravitational field strength is equal to 4 pi squared L, which is just a constant. It's the same in both scenarios. So 4 pi squared L is equal to a constant. So what we can do is t squared g on Earth and make it equal to t squared g on Mars. So t squared t1 squared g1 equals t2 squared g2. So the first one we'll do the Earth. So the time period on the Earth is 1.42 squared. So 1.42 squared times g1. Now we could say 9.81, but I'm just going to call it g. You'll see why in a moment. Equals time period on Mars squared. And it's 0.37 times the gravitational field strength for the Earth. So I'm going to times 0.37 times g. So the g's cancel. And then I've just got to get t2 squared on its own. So if I do 1.42 squared and divide by the 0.37, that gives me t2 squared, and then square root to give the time period. So if you calculate that, that should give 2.3 seconds. Hopefully that went okay. You might have done that in a different way, but hopefully you got the same answer. Let's have a look at the next one. So this one, straightforward. A simple pendulum and a mass spring system, so that's from last lesson, lesson 4, are taken to the surface of the moon. So what would happen to the period of the pendulum? And what would happen to the period of the mass system? If you want to have a go at this, please do. Then I'll take you through the answer. So the pendulum's t equals 2 pi root L over g. So the period of the pendulum, the moon has got less gravitational field strength, so the period of the pendulum would increase. So A would increase or go up. Period of the mass spring system, so we looked at this last lesson. T equals 2 pi root m over k. The spring constant is not affected by the gravitational field strength, so the time period will not change, it will be the same. Pretty straightforward. But a common exam question. Let's have a look at the next one then. So we had a question like this in the last lesson, but it was for the mass spring system. So if you want to pause and have a go. The length of a simple pendulum is decreased by 800 millimeters. The period of oscillation is halved. What is the original length of the pendulum? So t is equal to 2 pi root L over g. I'm going to square it all. So t squared equals 4 pi squared L over g. And then I'm going to rearrange to get t squared over L equals 4 pi squared over g, which will be a constant because this pendulum is in the same location for both scenarios. So the t squared over L is what I'm interested in, and we can look at that for both scenarios. So we end up with time period 1 squared over L1 equals whatever the time period 2 is squared divided by length 2. So I'm going to clear the screen and then write this out again, but in a different way, so make sure this is written down. So in the original scenario, we've got time period, so I'll just call it t squared, divided by the original length, which we will call L. I'm going to make that equal to the time period in the second situation, so the period of oscillation is halved, so it would be 0.5 t squared, but we have to do 0.5 squared as well as the t squared, so 0.5 squared is 0.25 or 1 over 4. So I'm going to have t squared, and I'm going to put the 4 at the bottom. Then we need to multiply by the length, and the length in this instance is the length minus the 800 millimeters, because it decreased by 800 millimeters. So we can bracket the original length minus 800. You can see there that t squareds will cancel, and I'm going to flip both sides and then multiply out the bracket and rearrange to find L. So L is equal to, I've got 4L minus 800, so 4 lots of L, minus 3,200. I'm going to put the L on the right hand side and the numbers on the left hand side, so that gives 3,200 equals 4L minus L is 3L. So L is equal to 3,200 divided by 3, which gives 1,067 millimeters. Hopefully that went okay, you followed that one. Or even better, you got it right in the first place. Let's move on to the last one. So what I'm going to do is to plot t equals 2 pi root L over g. You can manipulate that in any way you wish, onto a graph where you choose the axes yourself. The axes can be whatever you think's best, and show how you could calculate the gravitational field strength from your graph. So if you want to pause and have a go at that. So what I would do if I'm doing this, I'd get the original equation and multiply and square it, sorry. So I get t squared equals 4 pi squared L over g. And then it's pretty straightforward actually. I would plot t squared against length. And if you look, so that's on the y-axis, L's on my x-axis, 4 pi squared over g is my gradient. It's in the form of a straight line. It's plus 0 for plus c. So it's a straight line, positive gradient, that goes through the origin. So like this. And as it gives on the left hand side, the gradient, I'm going to call it gradient, is equal to 4 pi squared over g. So g would simply be 4 pi squared divided by the gradient. G is equal to 4 pi squared divided by, I'll call the gradient m. Hopefully you got that, or something similar. Thanks for watching, I'll speak to you soon.